So 15.5, we're going to study parametric surfaces here. So this is just, take the idea of a parametric line and just bump it up to the next dimension. So when you think about, right, a parametric equation of a line, let's just assume we're in the plane, right? Let me just call them x of t and y of t. Right, so the idea is you got some parameter t that ranges from some a to b. Right, and you think, so the idea is, somewhere over here you have your t-axis and your range from a to b, right? And as t ranges from a to b, this gives you a curve in space, right? So the x coordinates are just controlled by that x of t function, and the y coordinates by the y of t. And so we're just going to step up one dimension in each place. Okay, so we're going to, rather than take an interval here, we're going to move to a region in a plane. So we're going to do, call it the u and v. Okay, and so you'll have some region there. Could be, a rectangle. Could be something else. And then the idea is that over here, right, for every point in this region, you're going to assign functions, I'll just write it like this, x of uv, y equals y of uv, oops, z equals z of uv. Okay, and so I'll just say, generally we're going to, rather than work with it this way, we're going to view this as a vector valued function, but with two inputs instead of one, and so it'll just be that x. Okay. And so the point is that, right, you just have, as you input different u's and v's, you just get different places in space. And so you could kind of think of, in some sense, right, the idea of a parametric equation of a line is you're just taking this interval, you might be stretching it or shrinking it as you move over here, but you're just taking that straight line and laying it out somewhere, right? Here, you're taking this region and you're sort of deforming it and putting it in space, right? And so the x and y values are going to move around, the z values are going to move around. And so this is just going to correspond with some surface in space, if that makes sense. So you'll get some surface in your x, y, and z. Okay, so again, that's all pretty vague. So let's try a specific example and see if we can get used to this. So I'll just say sketch the following. We'll do at least a couple of these. The first one I'll just define this. X equals sine of v, y equals u, z equals cosine of v. So a lot of these are going to be standard problems that you'll see, standard types. All right. So remember back when we worked with parametric equations of lines, or of curves, our first thing was to try to define this, redefine it, or eliminate the parameter and write it as a curve, or write it as a function in x and y. And so you can kind of try to do the same thing here. So for instance, right, notice that there's just v's in the x and the z, right? And then there's just a u and the y. So the y and the x and the z really aren't intertwined much at all, right? You can basically put any u you want, but the x and the z for a given v are going to be intertwined with each other a little bit, right? And so what equation do the x and the z, I said x and v, I meant x and z. What do the x and z satisfy? What
X squared plus z squared equals to 1.
Okay, good. So essentially here's what we have, right? We have x squared plus z squared equals 1, and y can be anything, right? X and Y, or X and Z always satisfy this, but Y can be anything, so what kind of curve is that? Or solid surface? Cylinder along the
Why?
Y-axis, right? So this should be, it should correspond with your circle of radius 1 here, right? And then we just drag that along the y-axis. Again, I'm not too worried about how perfect it is, as long as you demonstrate, you realize it's that going on. That's all we're looking for. Does that make sense? Okay, so let's try a couple others here. Let's see. Oh, let's try. So these are all pretty similar. This time I'm gonna write it in this vector form. So R of u v is the vector valued function. Let's do v sine of u, v cosine of u, and then v. And if you finish that one, let's try basically the same idea. So try to come up with equations for both of those. You now, right, should be able to, use the fact that x squared plus sine squared is something, but now the z, like all three variables should come into your equations. So you want an equation in terms of x, y, and z that gets rid of the u and the v. Okay? So play around with that. Again, you're just using the same, right, same things you already know. Okay, so, have we made any progress yet? What's this one? What equation satisfied? So,
Squared equals to z squared.
okay, x squared plus y squared equals z squared. That's good. So, what is that equation?
A
A cone.
cone.
That's good. So remember, I said before, it's really worth memorizing that that one's a cone, right? Square root of x squared. And so that's the cone up here. Technically, on this one we just did, we actually have the bottom half of the cone too, right? Because you have z would be plus or minus. I'm just going to draw the top piece. But that's all there. And most of the time when we do these, we also have some bounds on what the u and the v are ranging from, so we get just certain pieces of these curves. Okay, so similarly, this one, what?
Z squared plus y squared equals 2x.
Yeah, so x in this case is y squared plus z squared, is that okay? So what's that graph look like? So parabola is coming out of the board, right? So you got parabola this way, that one's hard to draw, parabola that way, right? And so you just have some version of that, right? Okay, again, you don't have to be perfect in your graphs, but just know there's some paraboloid opening that way. Does that make sense? So it'll be important what what U and V are here. I'm just assuming U and V are anything, and you get these equations, but we'll come back to that in a second. Let's see. Oh, let me give another example. So express let's do y equals x squared plus z squared as a parametric. Actually, let's do it to sort of the most basic way. Okay, z equals x squared plus y squared as a parametric equation, or a parametric surface. Okay, and I'm going to do this two different ways. One way, we'll get a pretty picture. One way, we'll get an ugly picture. Okay? And I'll show you what I mean by that in a second. But just see what you can come up with first. Go from there. So, anybody come up with one? It's same as that one, but with things moved around. So this is actually the nice looking one. Let's look at this. So R of UV could be what? V sine of U, comma, V cosine of U, comma, V squared. Okay. Now I like that one, but let me say there's really an easier one you could have done as well. I'm going to call it, let's call this R1, and we'll call this one R2. This one's easier because Z was a function of X and Y, right? So you could always just do X, Y, X squared plus Y squared, right? That's another way to relate the two. Now, that one's very nice and easy to write down quickly, right? But you'll see there's a drawback to it. And so let me pull up the Mathematica and show you what some graphs of these things look like. Okay. So again, what's this guy look like? It's just that thing only up, right? So it's this bowl opening up like that, right? That's terrible looking parabola. So anyways, we get that kind of shape, right? This bowl opening up. And so I think I put my U's and V's in the opposite order. It doesn't make a difference, right? Your U's and V's can be switched around and it won't make a difference in terms of what the curve is. It's just which parameter. Again, I don't know why this is clean enough. Let me move this over. Let's see the whole thing. All right, and so again, we're not too worried about you guys doing anything too detailed with Mathematica, so don't get bogged down, but here's our parametric plot, all right? So we're going to graph this, and so look at this one I have, right? U squared, U times sine, U times cosine. Like, same thing, right? It doesn't matter if you flip those two, you're still spinning around. And then I put bounds on my U. So my U goes from 0 to 1, right? And my v goes from 0 to pi. So let's think about what the u is doing. I guess I got it backwards. Here, let me switch. Let me switch to the same variables I used, so I can refer to it. So v, u, v, u, v squared, and then I need to change these. U. Okay. So the v here now is ranging from 0 to 1. And so what's that going to do? It's going to make our z values range between 0 and 1, right? And then it'll go out here. And remember, if this was gone, if you fix a v, those give you circles, right? For every v, you get bigger and bigger circles as your v goes up. And so you'll get circles, and so that's what the bound here going between 0 and 2 pi, right? That'll create that whole nice circle across so that you'll wrap all the way around. So the v is just controlling how high up we are, and then the u is controlling to make sure we spin around the whole thing. And so let's look at that graph and make sure that it turned out right. Okay, so there you have it. And you can kind of see as it lays this out, right, there's a grid on here. And so each one of those horizontal lines, that's corresponding to a different u value, right? And then the vertical lines are corresponding to different v's. Well, that's not quite right. But hopefully, at least the vertical line, or horizontal lines are at least corresponding to these different heights of u. Okay, now here's that other one. Again, I think I changed. I'll just switch to what we had. X, y, x squared, oops, y squared. And so this time, right, it's pretty hard to describe circles in rectangular coordinates, right? And so sort of the easy way to describe that is just fix bounds on these, or changing to x and y, fix the bounds on x and y, and so range from whatever to whatever. And when you graph this, you see you get this thing, right, which is not exactly what we think of as this curve, right? It is, it's the curve, but since you're just setting the x and y bounds, you sort of lose that top half, where this is a much more natural way, right? That top one is a much more natural way to think of that curve. Does that make sense, rather than cutting these out? So parametric equations for surfaces are going to be great. We're going to do a lot with them, but we have to be careful. You know, even though this really is the simplest way to describe it, it's hard to set the bounds to get the shape we want, whereas this one kind of, it's easier to set the bounds, if that makes sense. Okay? So, let's try a couple other things here. So, when you're working with, if you want to work with planes, they're actually really easy to describe. And so let's look at that. And so, all right, so the way we're going to think of planes this time, we're going to have some point, I'm just going to call it r of 0, which is some point x naught, y naught, z naught. Now, when we talked about planes back in, I guess it was 2 chapters ago maybe, right? We came up with equations of planes. We always wanted a point, and then we wanted a normal vector, right? So we're going to change things up a little bit. If we're allowed to use parameterization, we don't need a normal vector. We can just get 2 vectors that are in our plane. Let's call this one W1. I'll just write it like this. A1, B1, C1, and then W2, A2, B2, C2. So now I want to think of the plane that contains those 2 vectors, right? So I go through this point, and then I want the plane that just contains these. So let's, right? So I want that plane that spreads out like this. So if you know those vectors are in the plane, how would you get some random point? Well, you could just say, right, I know I need to be here, and then I follow this line a little bit, and then or this vector a little bit, and then I follow the vector W2, right? And every point should be able to be described like that, where you follow some amount in this direction and then some amount in that direction, right? And so that's all we're going to do to describe a line, so, the plane. So the plane, equation of the plane. Should just be R of uv, and so it's your starting position, the R sub 0, right? The vector, I called it R of 0 here. Okay, so you have that starting vector, it's really just a point. And then you go, like I said, you can go some amount in the direction of W1, again this could be backwards, but that's just U times W1, right? And so you can go as far in that direction as you want, and then you can go as far in the W2 direction as you want, so V comma W2. Okay. And so notice this is exactly like your equation of a line, right? You've just thrown in an extra component. So if you drop this, that's the equation of the line down W1, right? And so if you want a plane, you just throw in this other component. And let's look at what this would look like. So I would just memorize the formula in that form, but in terms of our variables here, it'll be what? X naught plus UA1 plus VA2, right? And then Y naught plus U B1 plus B, oh, sorry, yeah, no, B1, B2. And then Z naught plus U C1 plus V C2. Does that make sense? So that's a very easy way to describe a plane then, especially if now you have lines inside of there. And so let's just do an example. So find a parametric equation, let's just say a vector equation. For the plane through, I'm just going to label these points so I can call on them later on. Okay, so 2, 0, 1, 3, 1, 2, and 2, 2, 5. Okay, so think about how we got equations of planes before. This time we really want, let me just write it like this. So P to Q, P to R. Again, I'm not paying attention to these points. I'm just saying if you got 3 points in space, they're going to form 2 vectors like this, right? And so you'll use that point, and let's just use P. You'll form the vectors from P to Q and P to R, and use those as your W1 and your W2. Okay? And then this should be even easier than writing out the equation of a plane from before. Oh, I just erased what we wanted. All right, so give it a shot. Alright, so what did we get here? PQ is
1,
111, PR is
0, 0, 2, 4.
024. And so the equation of our plane, let's just call it R. Again, it'll be of two variables, u and v, is just starting point, which was 201, right? So I'll leave more space than we really need, and I'll even write it in 0. So 201, and then you just add each component of the vectors, right? So it'll be plus u, and it doesn't matter, right, which one you pick, but we'll do u times 111, right? So that'll give you a u in every component. And then
0.
no v's in here. So again, you don't have to write this 0v, but I'll just write it down for now. And then 2v and 4v. Does that make sense? Okay. So we'll come back to tangent planes in a minute, but this will be a nice way to describe planes, especially tangent planes of surfaces that we come up with in this form. Let's go back to something you did, I guess it was in Calc 2. Surfaces of revolution. So let me just remind you what you had. So suppose you had, that's going to make our life easy. Suppose you had some function like this, f of x, right, and it went from some a to some b. And so one of the first sort of applications of the integral that we had, well, you did areas of underneath curves, and then the next thing, or one of the next things you looked at was solids of revolution, right? And so it was take this region bounded by this curve and revolve it around the x-axis. What do you get? What kind of shape do you get if you do that? So take this whole region, revolve around the x-axis. What do you get? I mean, I don't know that there's a nice name for it, but just describe, or try to draw, I guess, what you think it should look like, and then if you think you have a name for it, go ahead and chart it out. So, let's just go ahead and do this. So you should get something more or less like this, right? Some big kind of cone open, but it's, I don't even know what you call it, a horn, I guess. Looks like the end of a tuba or something.
I don't know, I was seeing a volcano on its side.
Now, come on. Who has ever seen a volcano on its side? That's just ridiculous.
I mean, if you tilt your head.
No, that's all right. I like that. Okay, so now the idea is, how could we describe this region using, or just describe this surface, right? So just the outside surface, not the ends, but the outside, the spiral piece of the surface, in terms of parametric equations. Because if you remember when you encountered this, we kept computing volumes and stuff, but we never came up with formulas for what those surfaces look like, and they show up all the time. So it'd be really nice to be able to come up with an equation. Remember, here's our x-axis, in this case, here's our y. Our z is coming out of the board at us, right, in this situation. And so, I'm gonna just get us started. So I'm just gonna let my x be the u, okay? And where do I want that x to range from?
A to B.
A to B. So my u is just gonna go from A to B, right? Okay, and so now, how do I describe the y and the z's here? I want this height, what's that height? F of, so at a fixed x, that's f of x. Well, let's go u in this case, right? So I have a height of f of u here, and I want a circle of that radius that spins around in the y and z component. So how do I parameterize a circle of radius f of u? Sine and cosine of the other variable, right? So that's where the v comes in. So f of u times, I'll do the sine, it doesn't matter. sine of v, comma, f of u cosine of v, or vice versa. Right? The sine and cosine could be swapped. Does that make sense? So this way you're going to get the u's and the v's will spin out a circle. I mean, sorry, the y's and the z's will spin out a circle of radius f of u, which is what you want to have happen. And then what should be the bounds on that v?
From 0 to
0 to 2 pi will give me 1 revolution, right? So 0 to 2 pi. Okay. Good. So actually, let's take a look at this to see that we get what we want. So here, let's just do it with a specific example. Let's say fine. So find a set of parametric equations. I'm just going to say a parametric equation of the circle or of the surface obtained by rotating f of x equal to the square root of x, and let's just say x ranges from 0 to 2 about the x-axis. Okay. All right. So follow what we just said the equation should look like, and then once you get it, I'll plug it into here and we'll see what that looks like. Okay. So what's our equation here then?
X equals to z squared plus y squared. Right.
Well, I mean, so that, I guess, that would be fine. That would give you an equation. That's not, I want a parametric
Oh.
equation. I want it in this form. I just want to follow what we did over there. And actually, it should be,
V
not
squared.
quite, it should be,
V sine u, V sine, V cosine.
oh, so you can do that. Let's just do it this way. U, and then
There's u.
square root of u, sine of v, comma, square root of u, cosine of v, right? And then the u's range from 0 to 2, and then the v's range from 0 to 2 pi. That make sense? So let's just confirm that this is what we think it should be. So u, 1/2 sine of u, cosine of v, and then comma u again to 1/2 cosine of v, X and y in there, u. Okay, so this should give us that same region, right? And so that, again, this setup here, the x-axis is coming out in this example. I should have labeled the axis. That's all right. But you get the idea, right? So if you view it right, twist. I think the screen is skewed too much, but anyways, there it is. Right, there would be your, y, in this case it's actually z equals square root of x, but then you can see, right, then we revolve that around the x-axis. So this is a handy way to sort of get our hands on those surfaces that we had talked about back in Calc 1 without a whole lot of work, right? We can do that pretty easily. All right, and so let's do this next. Okay, so tangent planes. Okay, so we have some surface here, which I'll say this is defined by r of uv, and let's just write it here. So it's of this form, right? X uv, y uv, z uv. Okay. And so again, even though we've described this surface parametrically, we should still be able to ask about a tangent plane, right? Surfaces have tangent planes at most points, unless they're, really poorly behaved. And so, do you remember how you found equations of tangent planes when you had a function of, when z was a function of x and y? I don't remember if we've done that in this class or not. So your tangent plane equation was z, so this, in this case you had z was some f of x, y, right? And you did f sub x at your point times x minus a, you remember doing this? Plus f sub y at your point y minus b, and then plus f of a, b. And maybe you use different, x naught, y naught or something, but that was the idea, was partial derivative times, right, your change in x, partial derivative times your change in y, and so on. This is essentially the same thing that we did that we're doing before. This is sort of your fixed point in space, and this way we're just describing them in terms of the z's. You had a fixed point in space, and then you're telling what slope to head in the x direction, x direction, and what slope in the y direction, right? And so, we essentially will do the same thing here, except for we don't have sort of a natural x and y direction to move on. We have directions to move on as u and v change. Okay? And so if you take the derivatives of this r with respect to, and we haven't really defined what this even means, but I think you can guess, r sub u, right, you take the derivative of x, y, and z with respect to u, right, they're all, you can take partial derivatives, you'll get a vector that's pointing sort of parallel to how you'd move in one direction. And that is actually a good place to come back to these lines. So when you look at these graphs that we've done, right, all of this gridding on here, if you're at a point, right, the r sub u and the r sub v just correspond to the vectors that sort of point in the directions of those grids. And then they're on the surface of your solid. So again, I'm not going to figure out exactly what this one looks like. Let's say that r sub v is really long here. But the point is, right, you'll have two different vectors that you can pop out by taking the respective derivatives, and they're going to point parallel to your plane, or parallel to your surface at that point, and so they should correspond with your tangent plane. And so you just, use RU and RV to find the tangent plane. Okay, and so if you're going to come up with a, a vector valued equation of your tangent plane, you can just use them like we used the W1 and the W2 before. If you wanted to, come up with an equation of a plane like we did before, like the old you know, a times x minus x naught, y times y minus y naught. You needed a normal vector then, right? So I'll just put in parentheses if you want the normal vector, use, right, so just like before, you can just use the cross product of those two vectors, and that should give you a normal vector to that point. Okay. All right. So let's just do, I guess we'll do one quick one. So let R be u cubed, v cubed, u plus v, and find the tangent plane at -1, 1, 0. So think about what those things mean for a minute. See if you can plot this guy. Actually, I guess you don't need to plot it. See if you can come up with the equation. You really don't need to know much of what's going on. Alright, so hopefully we'll do something here. So again, all you're going to use is this point, right? And then you just compute the R sub u and the R sub v. So what's R sub u? What's R sub v? So R sub u is 3u squared, comma, 0, comma, 1, and R sub v, 0, 3v squared, comma, 1. Everyone okay with that? All right. Now, I kind of waved my hands at this before. We have a point here. So this is a point, right? This is x, y, z. It's a point in space. It should correspond to a certain u and v values. What are they in this case? -1 and 1. Be careful, they're not necessarily just what was here, right? It depends on that function, but you're just saying, okay, -1 has to be u cubed, and so u is -1. You can solve it immediately. But if they were more complicated, then just be careful. You have to make sure you're finding a point that corresponds to this when you plug it into all three, right? So this one wasn't so bad. We came up with that, and so then our tangent plane should be, right, t of uv, well, it's our starting point, which was -1, 1, 0, right, plus u times, oh, I guess I should be careful here. So I need to evaluate these guys at the point in question, right? Oops. And so what do I get?
3, 0, 1.
3, 0, 1, and
0, 1.
0, 3, 1, good. And so now when I plug those in to the tangent, to the equation of the line, I do u times this guy, right, and then v times this guy. And so it'll be 1 plus 3, or -1 plus 3u, does that make sense? And then also plus a u over here, and then v times this, so it'll be 0 of them here, plus 3v there, and plus a v there. Does that make sense? And so, I guess sometimes people are bothered by reusing u and v, but they're just parameters, right? So you can reuse them. In fact, you want to here. Is that okay?
So it's just a tangent plane of u
So-
and v, so we don't need to use x and y, z to replace like.
No, I wouldn't bother. I mean, that's what I was saying. I would write your equation of your plane. If your surface is already given to you in a parametric form, I think it makes sense that your tangent plane is given to you in a parametric form.
Okay.
Whereas before we had z equaled f of x, that was in rectangular, your standard coordinates. I think it makes sense that you get the standard sort of equation
So
of a plane.
in fact here we don't need to calculate the normal vectors,
Right, yeah, you don't need the normal vector at all.
right? Okay,
The normal vector is only needed if you're going to go back to the old form of a plane.
gotcha.
And so I sketched this thing here just with Mathematica. Let's see. So we're at, I don't even know which, I should have labeled my axes. Doesn't matter. But we're at this, I couldn't get this plane to come up on top of there, but there's the tangent plane. It's just going to brush on that curve somewhere. I don't know which one's. It's a -2, 2, somewhere like this. So you're just in there, and you can see if we could embed that on top of there. I couldn't get them to plot on the same graph, but the tangent plane is coming out the way we would expect it to look roughly. Okay. What else? Let's just do one other thing here, I guess. All right, recall if you had two vectors, let's say u and v. What is the magnitude of u and v equal? So it's the magnitude of u times magnitude of v times sine of theta. You might remember that, but it also corresponded to what area of the geometric shape? What was it? Area of, trying to draw those parallel, of that parallelogram, right? So this was the area of the parallelogram. Okay. And so now if you think about how might you approximate the area of a surface, right? Well, if you just compute the areas of all those, so each little point on the surface, you could approximate the surface area by taking the r sub u, the r sub v, right? and then finding that parallelogram that those two vectors form, and use that to approximate the area of your surface. Does that make sense? So your tangent plane essentially, each little piece gets approximated by the area of the tangent plane that would sit over it, and then you add those all up. And as always, whenever we add up a bunch of things, integrals come out, and so I'm just going to write it this way. So surface area. Apparently I'm just going to keep writing surface area in different sentences. Surface area is equal to the double integral over your d of ds, and so in this case, it just becomes the magnitude of the cross product. Okay? And so that
So what is the range?
the d is this corresponds with your u and v domain, yeah. For the part of the surface you want to, you need to know where u and v sort of float around, if that makes sense. So let's try just one example here. So find the area of R, we'll just do an easy one here, 2u plus v, comma, u minus v, comma, 1/2 u, where okay, so check the bounds. We have a fixed bounds for u here. U goes from 0 to 1, and then the v goes from 0 to 1 minus u. Right. So again, just like before, you don't need to necessarily have this drawing, but here's our region, right? U goes from 0 to 1, and then v goes from 0 to 1 minus u. So you have this little region you're integrating over, but you're going to just compute r sub u, compute r sub v, take their cross product, take the magnitude of that, and then integrate it. And so hopefully I picked one that's easy. I think we just get constants, right? Yeah. So this is easy. So everybody's getting. Be careful, right? I just picked an easy one here, but there could be u's and v's in this equation when you're done, right? So just take the cross product with those in there. It is hard to get one set to give you nice values if they're much more complicated though. So what did you get for a cross product here?
-1/2, -1/4.
Negative 1/2 power.
I think it should be positive 1/2, right? It'll be 0 minus the negative, so 1/2. And then the middle one will be 0 minus 1, but it's negative, so 1, right? And then -2 minus 2, so -4. Is that what you got? Question?
Oh, so usually first. And usually.
Yeah, I mean, it doesn't matter. If you did it backwards, you'll just
Yeah,
get,
I
you'll get
did.
negative, the magnitude will be the same. So
Yeah.
if you did it the other way, that's fine, leave it like
Okay.
that. Because all we care about is we're going to integrate the magnitude. And again, in this case, it's 1/4 plus 1 plus 16, right? So what do we get there? 16, so 64 plus 69, is that what you said?
Yep,
Okay, so 7 halves, right? Or
Huh?
7 halves, right? I was thinking of a problem I did yesterday that had 49 pop out nicely, so it was in my mind. I was like, oh, that works out nicely, but it was not this one, it was a different one. Must have been for the other class. So if you sit in on the other class, my Calc 2, at some point today, I'm sure I have a square root of 49, because I remember doing that when I was preparing notes. Okay, so then we're almost done, right? I guess I erased it, but the surface area is just the double integral over your region of that. And again, we can't clean that one up, so we just leave it like that, right? And so this one's pretty easy, so they're already just given to you basically, right? 1 minus u, square root of 69 fourths, dv, du, just be careful there. And then, I think I'll leave that, it's an easy double integral, right? Okay, so let's stop there for 15.5.